Okay, I think we can start. So, hi, welcome to the next practice session for the Generative Adversarial Network. I'm T. Songjin Park, and today we will cover the basic concepts of GAN and implement the vanilla GAN, which is originally proposed by the Goodfellow and in Europe's 2014. And we will give basic skeleton code, which include training structure, and then the next one is the sample visualization, and then the FID evaluation. So you should implement generator and the discriminator architecture, and then you will also implement the noise sampling, and then you will design the GAN loss. So, all right, so I just uploaded the attendance check link, and if you don't fill it yet, please fill the attendance check form, please. All right. So in addition, we will give you the DC GAN, which is the basic GAN architecture code that you can enjoy by yourself. So if you have any question, please feel free to ask by using your mic or just chatting, or anything is fine. And you can ask anything about the lecture or the previous practice session, or either anything is fine. So please feel free to ask about anything to me. So before we go, there are some preliminary steps we should do before we start the practice session. So first of all, you should upload the files which I uploaded in the classroom using this button. Okay. All right, I forgot to prepare the file in my laptop, but you could find the inception.
올려놨어요.
네.
그 진동 12개였어요.
저 민덕기님
네.
마이크가 뮤트가 안 돼 있어서요. All right, I manually mute him, so sorry. All right. I will mute all before we start. 네, 제가 이거 일괄로 뮤트하는 그 버튼 못 찾겠어가지고, 혹시 지금 뮤트 안 돼 있으신 분들은 음소거 일단 부탁드립니다. So keep going. So you can find the file, two Python file in which I uploaded in the classroom, which is the inception.py and the fid.py. So please upload the files to the Colab by using this button. So you can choose the files, you can press the files, and then you can find this button. So upload to the session storage, and then you can upload two Python file to the storage. So yeah, this is the first preliminary step. And then let's move on to some other additional preliminary steps. So before we go, we must check the GPU is we can utilize the GPU. So please run the first code, this one, and then you can see some Tesla T4 and maybe some NVIDIA P40 or P400, then everything goes fine. So if you don't see anything after run this code, then you should select the runtime, and then press the change runtime type, and then you should select the GPU in your Colab. All right, I believe everyone check this one, and then just run the following codes So these two blocks will prepare the Python package, which we'll use in our practice session. And this code also create some folders which we use in the practice session. So just run this code, and then the second preliminary step is define the visualization and then the image saving codes. So same as before, you can just run those codes like this. And I will not explain deep about this code because this is just about how to use the pyplot in the Python. So you can find how to use the pyplot is in the Google Awesome Stack Exchange. So I will skip this session. And the third step of the preliminary is the loading the data and define the data loader. So in this class, we will use the MNIST, which is the data set of the handwritten images, handwritten digits, and this is the samples which exist in the MNIST dataset. 네, 출석 링크는 혹시 제가 확인을 못한 상태라면 다른 분들이 조금 업로드를 해주시면 좋을 것 같습니다. 네, 저도 주기적으로 보면서 업데이트 하겠습니다. Right, so in this practice session, we will use the MNIST dataset because the Goodfellow used the MNIST, and MNIST is comparatively small size dataset compared to the other dataset. So due to the time constraint, we will use the small size MNIST for the practice. And you can also use the CIFAR10 and any other kind of the big size of the image dataset if you are interested in. And as you know, the CIFAR10 is already implemented in the PyTorch, so you can simply use the dataset equal CIFAR10, then the code automatically download the CIFAR10 dataset instead of the MNIST. All right, so same as before, just run the code. I will briefly explain about the code. So dset.mnist use the package we defined here. So this is about, all right, I will mute. Oh, no. Okay.
아무나 저거 없었어. 에이, 당연히 안 했지, 씨발 저거 그냥 가라.
죄송합니다. 이게 뮤트가 한 명씩밖에 안 돼가지고 혹시 지금 수업 듣고 계시는 분이면 뮤트 꼭 좀 부탁드립니다. 질문하실 때는 마이크로 하셔도 돼요. 네. Alright, so we can download the dataset using the torchvision.dataset. The torchvision provides some collection of the dataset, so you can choose one of them if the torchvision supports that dataset. So using this is how we download the dataset using the torchvision dataset library. It's very simple. So you can just select the directory and then turn on the download and then apply some torchvision transforms. It can contain it might contain the resize or crop or some color jitters, any other kind of it supports any other kind of the torchvision transforms, but for now we don't need any kind of these image augmentation, so we just apply the toTensor, which is convert the image file to the tensor file. And then as you know, we define the data loader as before as similar to the practice sessions you learned before. All right, so this is the first part of this practice session. So in this part, you will define your generator and the discriminator. So this is some overview of the GAN, and your work is to implement the generator and the discriminator. I think I'm not sure you learned about the CNN. Have you learned about the convolution layer or something? 다음 주군요. Okay. So, as Goodfellow proposed, we will implement the generator and by using the multi-layer perceptron. I heard that you learned about the MLP maybe 2 weeks ago or 3 weeks ago. So your job is to implement the generator and the discriminator using the multi-layer perceptron, also known as the feed-forward network. So yeah, this is your job. So I will give you a little bit more details. So I will explain the discriminator first. So your job is to implement the classifier, which is the binary classifier. So your discriminator should predict the label, which is 0 or 1, and the input size will be the image in the MNIST dataset. So the size of MNIST dataset is the resolution of the MNIST image is the 28 by 28, which is the input of the discriminator should be the square of the 28. So the dimensionality of the input of discriminator should be 784. Yeah. So your job is to implement the classifier, which receive the 784 dimensional vector as an input, and then it outputs the binary label, which is the 0 or 1. This is your first job. And then your second job is implementing the generator module. So you can implement the generator. You can also design the generator using the MLP layers. So your job is to, all right, so your job is to implement the generator. So output should be 28 by 28 image, and this means your output should be 784 dimensional vector, and the input of the generator is some kind of Gaussian random noise. So in this practice, we will use the noise with the dimension 100 dimension. So your job is to receive the 100 dimension vector as an input, and the generator should output the 784 dimensional vector as an output. So I will give you 15 minutes to implement generator and this discriminator. So if you have any question, please feel free to ask me. All right, let's meet at 11 and 11:02. Oh, there's a question from the Joshua. So how many hidden layers for discriminator and generator should we use? I think is your freedom. So you can use you can choose any number of the layers. So yeah, maybe 2 or 3 or 4 is appropriate for the MNIST. But any number is fine. So please feel free to implement. Alright, I will show you my 네. 네, 학년님 감사합니다. 한번 확인해 보겠습니다. 제가 일단은 지금 뮤트 안 돼 있는 분들은 매뉴얼하게 다 뮤트를 해놔가지고 네, 다음에 한번 확인을 해보겠습니다. 감사합니다. Right, so I'll show you my solution and I will explain this code on 11. 네, 수업 이후에 저희가 짠 코드는 공지로 알려드릴 예정입니다. All right, time's up. So I think everyone can implement the code without the difficulty. So I briefly explain about my solution. So this code used two hidden layers, and then it maps the topmost layer to the 784 vector dimensional vector, and then apply the sigmoid because the MNIST is the grayscale image, so it must lies in the between the 0 and 1. So the code is very simple because the dimensionality of the input is the 100, and it first maps the 100 dimension vector to the 256 dimensional vector and apply the ReLU activation. And then it also maps the 256 dimensional vector to the same dimensional vector, and then apply the ReLU again, and then it maps to the 256 dimensional vector to the size of the image, and then apply the sigmoid function on top of the generator. And then there's one additional code which I didn't mention in the instruction. So you can just copy and paste this code because all right, I will answer the Haehyun's question after my explanation. So this code stands for the this code stands for the generation of the image, because the image should be represented as a channel by height by width. So we should map the 700, we should reshape the tensor of the 784 dimension into 1 by 28 by 28 to generate the image. That's it. So it's very simple code. And there's a question from Heian. Why you map the 256 dimensional vector to the same 256 dimensional vector? Yes. So yeah, it's because it's not that clear. This is not that clear because the MLP and any other some deep learning models are black box. So what's really happens in what we are not sure what's really happened in the some MLP layers, but the one thing we can ensure that is we apply the linear mapping from 256 dimension to the 206 dimension, and then we apply the ReLU on top of that linear layer, and it means the mapping is not just a simple linear mapping, and it's a nonlinear mapping to the same dimensional vector. So it means that the any kind of such nonlinear mapping could not be identity mapping, and such kind of non-identity mapping have some meanings in their model, but we cannot clearly understand what's the purpose or the functionality in that model. So 뭐 네, 제가 한국어로 좀 더 그냥 말씀을 드리자면 어쨌거나 네네 그 결국 이게 256차원에서 256차원으로 뭔가 저희가 리니어 프로젝션을 한다고 했을 때 이게 그냥 리니어만 있다면 뭐 당연히 아이덴티티 매핑이 되는 거 아니냐 이렇게 생각을 하실 수도 있지만 어쨌거나 이 렐루나 아니 뭐 하이퍼볼릭 탄젠트 같은 이 넌리니어 프로젝션 하는 그런 펑션이 같이 위에 얹어져 있기 때문에 결국 이 리니어 매핑하는 펑션이랑 렐루가 합쳐지면서 결국 널리니어한 그런 프로젝션이 될 수 있는 거고, 그런 널리니어한 프로젝션이 뭔가 아이덴티티 매핑은 아니면서 뭔가 유스풀한 피처를 뽑을 수 있는 그런 프로젝션 뭐 펑션이 될 수 있기 때문에 이렇게 같은 디멘전으로 간다고 하더라도 뭐 의미가 있을 수 있다라고 말씀을 드리고 싶고, 뭐 무슨 의미를 갖냐 그거는 명확히 알 수가 없다라고 말씀을 드리고 싶고, 그리고 이제 there's another question from the Eugene. So why do we use the feedforward layer instead of the comp layer? Because first of all, we did not learn about the comp layer because the comp layer is the topic of next week. So that's the first reason. And in addition, Goodfellow, which is the author of the 2000 this paper, which is submitted to which is accepted in Europe 2014, you also use the MLP layer in their experiment. So I think we can obviously use the FC layer instead of the comp layer, but using comp layer will show the better performance rather than using the FC layer. So at the end of this practice session, I prepared code for the DC GAN, which is the deep convolution GAN. So you can see this code and get some intuition about how do we use the comp layers to generate image and discriminate the image. Yeah. All right, let's move to the discriminator. So this one is also simple. So input should be square of the 28, and then it maps the square of the 28 dimensional vector to the binary value. So at the top of the discriminator, we apply the sigmoid function. And also, I forgot to mention this line because the input was the size of the batch by channel by height by width. So if you want to pass the input to the discriminator, you should reshape the tensor into the batch by 20 square of the 28. So this function does that work. So please copy and paste, or just write down this code into your code. And then also, all right, so there's a question from Seungmin. So why we use Rickel value instead of the normal value? So there's a dozens of reasons. So when you're using the Rickel value instead of the ReLU, it may depends on your model and your application. So the advantage of the Rickel value is it does not ignore the negative values compared to the ReLU, but the disadvantage of the Rickel value is I'm not clearly remember the disadvantage. So there's some leakage in the negative values are sometimes harmful to the model. Sorry, I didn't clearly answer your question, but you can use any kind of the activation function in here. So you can use the Rickel value or ReLU or hyperbolic tangent or any kind of like the GELU or any kind of the activation functions, but you should keep in mind that your choice should fit into your model. So in this case, this gives this example is extremely easy compared to any other some real world task. So you can choose any kind of the activation. I guarantee that it works well in our practice session, but if you are applying your model to some real world data, then you should understand your the characteristic of your data and carefully choose the activation functions of your model. So 네, 답이 됐는지는 모르겠는데 네, 그렇습니다. 그래서 리켈-렐루를 사용하는 거에 대한 장단점이 분명히 있고 지금은 그냥 뭐 큰 이유 없이 일단 리켈-렐루를 골랐다고 보시면 될 것 같습니다. There's question from the Hansung. So is there any advantage if we choose the different activation function for the generator and discriminator? I think it's a good question, but 네, 이 부분은 저도 제가 한번 서치를 해본 다음에 혹시 지금 뭔가 좀 이 겐 프레임워크에 퍼밀리어 하신 분이 뭐 답변을 해줄 수 있으시면은 뭔가 좀 공유를 해주시면 좋을 것 같고, 아니면 제가 서치를 한 다음에 클래스홈 같은데 다시 네, 업데이트를 드리겠습니다. 뭐 저는 큰 의도가 있진 않았고, 사실 이게 레퍼런스 코드에 리퀴렐루로 되어 있었기 때문에 그래서 사용을 한 것이었고요. 사실 저는 이게 리퀴렐루거나 렐루거나 보편적으로 잘 작동을 할 거라고 생각하고, 뭐 그냥 렐루로 해도 오히려 더 잘 작동할 수 있다고 생각을 하는 게, 사실 리퀴렐루를 썼을 때 아무래도 이 네거티브 밸류가 살아 있으면서 생기는 문제들이 또 있다 보니까, 그래서 그냥 이 렐루를 쓰는 게 네, 뭐 말이 안 되는 초이스가 아니다. 그냥 네, 그렇습니다. 일단 뭐 정말 솔직한 리즌을 말씀드리자면, 네, 레퍼런스가 위키렐루로 했기 때문이었고요. 그 자세한 이유는 제가 찾아보고 다시 업데이트를 드리겠습니다. Alright, I think everyone successfully implement their code and fully understand about how to implement the discriminator and then generator. So let's move on to the next one. So just run this code. This code will, right. All right, let's move on to the following section. So the next section is, before we move on, we must load our model, define our model, and load our model on the GPU. And also, we should define the optimizer for discriminator and the generator. So I think everyone already familiar with this kind of function. So just run the codes here. And your next job is to implement the noise sampling function. So I will give you 1 minute to implement the sampling of the noise. You can use the torch.randAnd, which is sampling the noise from sampling the value from the normal distribution. So your job is to sample the value, sample the vector from the normal distribution, which is the size of batch by dimension. In this case, we just use batch as a 128 and dimension as a 100. All right, I'll give you 1 minute for the implementation, and I will show you my solution. All right, I think it's extremely simple. So I will show you my code. So this is it. So you can use the torch.random function. So the first one should be a bit size, and the second one should be a dimensionality of their vector. And then load this to the GPU. Then you can sample the random normal vector from with the size of 128 by 100. All right, let's move on to the third section of our practice session. So in this section, you will train the GAN using the pseudocode, which is proposed in the Goodfellow's paper. So your job is to implement such pseudocode in the below section. And this is the objective, which the professor explained in the lecture. And this is the pseudocode, which Goodfellow proposed in his paper. So briefly read these two slides and then implement the GAN training codes below here. So your job is to fill the question marks here. And then I will show you how the codes run and the outputs are, what is the outputs. So I will give you 10 minutes to implement this code and we will see the solution. Right, I think everything needs for the implementation is included in the code. And if you cannot understand something, please ask me. And also I prepare some additional material and I uploaded in the chat. So if you are interested in the math lies behind the GAN, I recommend you to read this paper. This paper explains about some mathematics behind in the GAN and some limitations of the GAN at the time. And then it also connects the GAN to the Wasserstein GAN, which is the mathematically beautiful version of the original GAN. So if you are familiar with the mathematics, I recommend to read this paper also. So that's it. So I will show you my solution on 1138.
아, 왜 이래?
Right, we are running out of time, so I'll directly explain about our solution code. So the code on the right side is the direct implementation of the pseudocode. And for the simplicity, I use the k=1, but for practice, I remember that the Goodfellow used k=10. So you first train the discriminator for 10 times, and then we update the generator after the discriminator learns something from the data and some noise samples. So by the way, so in this practice session, we use k=1. So please be aware of that, and I'll explain the code. So, oh, sorry. Yeah. So after, yeah, so this is just some Gaussian random noise for some fixed random noise. So you could write down just as before, which we implemented here. And we define the criterion as the binary cross entropy because the objective of the discriminator is the binary classification, and we choose epoch as a 200. And then we will save the image in the list of the training progress image list. Right, this is the inner training loop, and the first code is training the discriminator, which is same as maximizing the log dx and log 1 minus dgz. Therefore, before we training the net d, we must clear the gradient in the net d, and then we load the data from the data loader, and we define the label as 1 because in this code line, we pass the real data to the discriminator, and the label of the real data should be 1 because the 0 means a fake and 1 means the real. So in this case, everything is the real, every input is the real image. So we define the label as a tensor filled with the ones, and then we pass the data, real data, through the discriminator, and then we apply the BCE loss on top of the output. So the output should be predicted as a 1. And this is just for the print function. So please ignore this one. And then move on to the next part. So we also maximize this one if the discriminator should predict false if the input was the generated image. So in this case, we generate the fake image first. So we, as before, we sample the noise from the normal random distribution, and then we pass the noise through the generator. So we get the fake image, and then we set the label as all 0 because everything should be 0 because the input image is the fake. So we set the label as a 0 tensors, and then we pass the fake image to the discriminator, and then we also apply the BCE loss on top of that. So the fake image should be discriminated into the fake false. And then after this code blocks, we sum the loss from the real image and fake image, and then we apply the backward, and then update the optimizer of the discriminator. All right, that's it. So this is the first part of the pseudocode, and as I mentioned before, so we choose the k=1 here. So we move on to the second block of the pseudocode, which is the update of the generator. So it is same as before. So before we update the generators, we must clear the gradient in the net G, because the gradient is stacked in this code line. So we should clear the gradient in the net G, and then and then we also apply the we also design the label as the ones, because the perspective of the generator, the discriminator should predict true when they pass the generated image. So in this case, for the training of the generator, we should design the label as a torch ones, and then we pass the same fake image through the net D, which is the discriminator, and then apply the BC loss on top of the model, which pushes the model to predict the generator generates the more realistic image. So after all, apply the backward, and then step the optimizer of the generator, and everything's done. And then the rest of the codes are just printing functions and some saving the outputs of the generated images. Yeah, that's it. So I think it's very simple and clear implementation of the pseudocode, and you can see the such progress when you're running this code. All right, that's all right. So there's a question from the Eugene. Can you explain again why did you use dot detach function for a fake variable? All right. All right, I will mute again. Yeah, so you mentioned the detach here. I see. Because it's the reason because we did not want to update the generator at the first part of the pseudocode, because the objective of the first part of the pseudocode is update the discriminator rather than the generator. So dot detach means that this fake image is detached from the computational graph, and then it means that the gradient doesn't flow through the net G. So we apply the dot detach on the fake image, and it ensures that we do not update the generator network while we training the discriminator network. So there's a question from another question from the Eugene. Sure, you can use the with torch.nograd when you are get some fake image. You can use the torch.nograd. I think. Yeah, I think that's more clear version of blocking the gradient to ensure that the generator network doesn't update during the training process. Yeah. 네, 그래서 노그라드로 하셔도 됩니다. 네. 네네. 그래서 한국어로 설명해달라는 말씀이 있으셔가지고, 네. 한국어로 좀 설명을 드리면, 저희가 여기서 이제 이 첫 번째 코드 블락에서 하고 싶었던 일은 결국 디스크리미네이터를 업데이트를 하면서 동시에 이제 제너레이터는 업데이트를 안 하는 것이었기 때문에 결국에 이 컴퓨테이션 그래프에서 디태치하기 위해서 이 제너레이터를 이 컴퓨테이션 그래프에서 디태치를 해가지고 이 그라디언트가 저 제너레이터로 흐르지 않게 인슈어하기 위해서 여기서 디태치를 썼다고 보시면 될 것 같습니다. 그래서 아까 유진님께서 말씀하신 게 그러면 톨시 노그라드로 해도 되지 않느냐라는 말씀을 해주셨는데 뭐 똑같이 네 톨시 노그라드로 하나 디태치로 하나 결국 백워드가 안 돼, 그러니까 그라디언트가 블락되는 거는 같으니까 네 뭐 같은 퍼포스라고 볼 수 있을 것 같습니다. 네 답변이 되었는지 모르겠네요. 네 예, 계속 넘어가 보겠습니다. 이제 시간이 거의 마무리가 될 시간이라 네 감사합니다. Alright, so let's move on to the final section of the practice session. So we define the sum plot functions at the top of the at the very beginning of our practice session. So if you run this code, and you can see some progress in visualize the progress of the training process. So you see that at the beginning of the training, the generated data are very unclear and something like the Gaussian noise. But as the training goes on, then you can see that the generated image are getting closer to some real handwritten digits. So you can check with your you can qualitatively check the code is working well. And we also, I will briefly introduce this section, and I will not explain deep about the FID and any other kind of the evaluation of the GAN. Yeah, so evaluation of the generation model is a bit hard in general. For it is usual for the image or text or any kind of the generative model always have some difficulty to evaluate the performance of the generated result, because unlike some discrimination or classifier, there's no exact solution or answers exist in the generative model, because the purpose of the generative model is just mimicking the probability distribution of the data. So evaluation of the generative model is always the hard problem. So one clear and simple evaluation metric might be the training loss, but it's not that clearly connected to the quality of the generated sample. So for the vision domain, some researchers are propose many kind of the evaluation of the generated image, and the most frequently using one is the Fresher inception distance, which is also known as the FID score. So I'll explain the FID score briefly. So before we go, so Fresher distance measures the distance between real dataset and fake dataset in feature space of the inception network, which is the pre-trained network which is pre-trained on the ImageNet dataset. So we first extract features from using the inception network, and then measure the Fresher distance with the features. So Fresher distance is originally designed to measure the similarity between two curves, but they use the Fresher distance in this paper, 2017. again trained by blah blah blah, written by Martin Hussel, use the threshold distance for measuring the similarity or just a distance between the two probability distribution. So the purpose of the FID is measuring the similarity of the real and fake data, the distribution of the fake and real data in the feature space. So that's it. So if you are interested in the details of the inception score or the FID score, I uploaded the link about some short article and the original paper here. So please check for the further details. So for the simplicity, I just bring the implemented one here. So you can check the detailed implementation of the FID score in here, or the file I uploaded in the files in 2 Python files in the zip file. So all right, so yeah, that's it. So the following codes are just measuring the FID score using the release this released code. So I think the details of the FID score function and the inception scores are not appropriate because we did not learn much about the FID score yet, and also the time runs out. So I hope you will. I think this is checking the code deeply is the take-home task. I will remain this as a take-home task. Yeah. So after running this line of code blocks, you can check the final FID score, but please do not trust this FID score 100% because the inception network is trained on the ImageNet, which is very different from the MNIST. So you might see some high FID score when you're running MNIST, while the generated image is still shows some realistic features. All right, that's it. So the last part of the practice session is the DC GAN. So I already wrote down the code about the DC GAN. So if you're interested, just read the paper and try yourself to implement the DC GAN. All right, that's it. So I think it's time to wrap up the practice session. So thank you for attending today's practice session, and I will upload the solution code on the classroom. And there's a question I cannot answer this time. I think it's question about Hansong, because so the difference of the why we use different activation function for the generator and discriminator. So I will upload the answer in the classroom after the class. All right. Oh, all right. There's one more question about when you update G, should we sample a new batch of noise and generate new sample since you already detached fake from the computational graph? All right. 저 이게 질문을 잘 이해를 못했는데 혹시 조금만 더 자세히 설명을 해주실 수 있으신가요?
혹시 들리시나요?
아, 네네.
Yeah, so what I mean is in the bottom part, when you update the second step, update the G network, right? When you maximize there. So here you are running fake through the discriminator network, right? But this fake was already detached from the computational graph. So when we backpropagate to it, it's not actually going to update the weights of G. So shouldn't we sample here, new noise, create a new fake samples, and then run them through a discriminator? So we actually improve the generator.
I see. So your question is why we use the fake image here, but so I understand your question. So actually the fake image here is not detached from the computation graph because if you all right. I think this is connected to the Eugene's question. So all right. So Eugene asked that why we didn't use the tools.nograph, because if you like this one, and then as sorry, what's your name?
Yeah, Rodrigo.
As Rodrigo mentioned, if you does this, then you should resample the image here because the gradient is blocked. Yeah, gradient is blocked. So you should resample the fake image to pass the gradient through the net G. But in this case, we just detach the fake image only at here, and the fake image is not detached because the fake image just detached in only for this line, and any other lines the fake image is not detached from the computation graph. So if you write the code like this, and then this ensures that the fake image is detached after this line of this code line. So the fake image should be detached in here and here, but without this line, the fake image detached in here, but the gradient is still computation graph is still alive in this code line.
Yeah, thank you. I understand. Yeah, I think problem was, yeah, I thought detach was an in place operation.
No.
Yeah, you're right. Thank you.
네, thank you. 네, 그래서 네, 아까 유진님이 주셨던 질문과 연결을 해서 이렇게 정리가 될 수 있을 것 같습니다. 네. All right. Is there any question? All right. So there's a question from the Hanyu. When you get the notice about the project, so yeah, I will ask to the professor about the project. I'm not sure when we announce the projects. Maybe it's I will ask to the professor. Yeah. All right. I think there's no more questions. So thank you for attending the practice session, and this is the end of practice session. So please feel free to leave the Zoom meeting room. Thank you.
감사합니다.
네, 감사합니다.